In this video, we're going to talk about free energy and entropy, the end of chapter 18. You can see by this picture, it looks kind of funny that a guy would be running uphill away from a boulder that's going uphill. That certainly would not happen spontaneously, but it could happen if you add a bunch of energy into that boulder through a catapult or a cannon or something like that. We're going to be looking at, are chemical reactions spontaneous or non-spontaneous? Spontaneity is associated with free energy, which we call delta G. So there's that delta again, final minus initial, whether it's temperature or heat like we've been talking about. How can one predict whether a reaction will occur under certain conditions in a given amount of time? We're going to use spontaneity to determine that. How can one decide whether a reaction at a certain temperature and pressure will be spontaneous? Spontaneous reactions take place without the exertion of outside forces. In other words, they happen by themselves. For instance, ice melts when you put it on the table at room temperature. Rust occurs on metals outdoors. Spontaneity does not relate to rate of reaction. It doesn't matter how fast or slow the reaction is. It doesn't determine whether something will happen spontaneously or not. So what is spontaneity? As you can see, it relates to free energy. The free energy of a system is a measure of the amount of usable energy, or energy that can do work, in the system. The concept of free energy provides us a measure of how much usable energy is released or consumed when a reaction takes place. Free energy depends on three main factors. Enthalpy, which we've talked about, delta H, referring to energy stored in bonds. It's the difference between the heat of the products minus the heat of the reactants. Also depends on entropy, which is the change of the system during reaction. In particular, referring to whether a system becomes more orderly or less orderly, more random or less random. Lastly, free energy depends on temperature, or the kinetic energy movement of the molecules in a system. There is a mathematical way to determine spontaneity, and that's called the Gibbs free energy equation, which you see here. Free energy, delta G, enthalpy, delta H, temperature in Kelvin, and you have entropy, delta S. The energy change for a chemical reaction, delta G, depends on enthalpy, which is the breaking of bonds and making of bonds. Depends on entropy, which is the randomness or disorder of a system. And it depends on the absolute temperature, Kelvin. The free energy equation is used to calculate the change in the free energy. Delta H is enthalpy, delta S is entropy, T is the temperature in Kelvin. Free energy combines enthalpy and entropy to measure the spontaneity of a reaction. There is our Gibbs free energy equation. Always remember to use Kelvin temperature. If delta G is negative, that means the free energy is released. The reaction is spontaneous, meaning it'll go on its own. If delta G is positive, meaning energy has to be added into the system to get the reaction to go, that reaction will be non-spontaneous. But the reverse reaction would be spontaneous. So let's do some examples mathematically to see this. Determine whether the following reaction is spontaneous. We have entropy at 138 joules per mole Kelvin. The enthalpy change, delta H, is negative 75.9 kilojoules per mole, with the system being at 273 Kelvin. So first let's predict. Here's our Gibbs free energy equation. If we predict, we said that we have the enthalpy is negative 75.9 and the entropy is 138 joules per mole. Notice kilojoules and joules, that's not going to work, so we're going to need to convert to kilojoules. The enthalpy is negative or exothermic, and the entropy is positive, meaning it's going to be more disorderly. Therefore, we predict that the free energy is going to be negative, meaning it will be spontaneous. So let's work it out in an equation. So there's our equation that we're going to use. The problem is asking for the free energy and whether it's spontaneous or not. And we're given all those other factors. So let's plug in the numbers. Enthalpy, we plug in minus the temperature times the enthalpy. But notice I had to change the enthalpy into kilojoules per mole. Divide by 1,000. That comes out to a delta G value, or a free energy value, of negative 114 kilojoules per mole. That is a spontaneous reaction, meaning that energy is released during this process. You can also notice it's exothermic. There was an increase in temperature. It's about 0 Celsius. It's an increase in entropy, where there's more disorder. Let's try another one. What if the entropy is negative 55, the enthalpy is negative 27 kilojoules, and the system is at 535? Again, let's predict using the free energy equation. Consider the units. They have to be the same, kilojoules. We have exothermic reaction, we have a more orderly reaction. The entropy is negative, meaning that it's a decrease in entropy, meaning it is more orderly. In this case, delta G could be positive or negative. It depends on how high the temperature is. And in this case, the temperature is quite high, 535 Kelvin, 808 Celsius. So this reaction we predict to be non-spontaneous. Let's plug in the numbers and see what we get. There's our equation. We plug in the numbers. Notice I converted the entropy to kilojoules per mole, and it comes out to a positive 1.93 kilojoules per mole. You should be able to go through and do these on your own. Just pause the video before you see the answer. That indicates a non-spontaneous reaction like we predicted, because energy has to be added in to get this to work. It is exothermic, but it's slightly exothermic. Temperature's high. It's a decreased entropy, meaning a negative times a negative gives you a positive free energy. Let's try another example. Now we have an entropy of positive 55, so more disorderly, and we have an enthalpy, delta H, of 452. Now it's endothermic. We're adding heat in, and it's a pretty low temperature here. So let's predict the spontaneity of this problem. Okay, there's our numbers. You can see that we have to convert to the same unit of energy, kilojoules. We have a positive enthalpy, so delta H is positive. We have a positive entropy. Delta H means it's endothermic. The positive entropy means it's disorderly. Again, we have possibility of free energy being negative or positive. It could be spontaneous or non-spontaneous. It's only going to be spontaneous, however, at high temperatures. 165 Kelvin is negative 108 Celsius. That's a low temperature. We're predicting this will be a non-spontaneous reaction. So let's plug in our numbers. As we do so, notice I converted to kilojoules. That comes up with a highly positive delta G value, meaning a lot of energy needs to be added into this reaction, so it's going to be non-spontaneous. It's endothermic. It had increased entropy, which means there's more disorder and more random, but remember the temperature was very low. Let's try one more. Entropy now is negative, so it's less entropy, more ordered. Enthalpy is positive, and the temperature is 115 Celsius. Notice Celsius there. Let's predict. According to this, we change to kilojoules again. Positive enthalpy, negative entropy. So we have endothermic reaction that's orderly. That's always going to give us positive delta G value, which is never spontaneous reaction. So let's work out the numbers. We plug them in here. Notice I had to convert the Celsius temperature to Kelvin, as well as convert the joules of entropy into kilojoules. We come up with a highly positive delta G value. That is a non-spontaneous reaction, which is endothermic, a decreased entropy, and as we said, it always produces non-spontaneous reaction. Notice I converted both the joules to kilojoules and the temperature Celsius to Kelvin. And lastly, here's a summary chart to let you go through the whole thing, which is what we talked about.